Thank you very much for inviting me. It's a pleasure to be here. Today I'll tell you about some techniques from arithmetic geometry and how we can apply them to problems in physics, and hopefully eventually work backwards and take techniques from physics and apply them to problems in arithmetic geometry. But right now we're only going one way. I try to keep the talk as basic as I can. So hopefully PhD students and people who don't work on this stuff can take something away from this. Although the experts might be a little bored. All right, I'll start with some motivation and I'll review some techniques from arithmetic geometry. I'll spend some time on this example of elliptic curves with complex multiplication, because many of the things we do in the more complicated examples involving Calabi-Yau manifolds are essentially this idea, but on steroids. We'll use this Zeta function, and we'll use this to find examples of supersymmetric flux vacua or rank 2 attractors. And finally, I'll end with some speculation on how we can go backwards, how ideas from physics can help us in arithmetic geometry. Okay, so what's the motivation for all this? It comes from, there are two examples in string theory. There are many more, but I'll focus on two examples where you end up studying the variation of Hodge structure of some family of Calabi-Yau manifolds or some varieties. And this is something that can link directly to problems in arithmetic geometry. So for some physics first, we're often in the situation where we want to study a family of Calabi-Yau threefolds. Usually this is in some kind of string compactification. So for example, you take type 2B string theory, you compactify on a Calabi-Yau manifold, and this Calabi-Yau manifold will have some moduli. So it can be deformed in some way while still keeping a Ricci flat metric. And in Kaluza-Klein compactifications, these deformations are moduli, so they correspond to some kind of massless scalar in the effective 4-dimensional theory. For example, this is one of the most famous examples. It's this one parameter family of quintics. Usually people will take a quotient of this and resolve it, so you get really something with one complex structure deformation, but that's not so important in this example. So changing psi will typically give a diffeomorphic manifold, but with different complex structure. So you got some nearby psi, you're not changing too much of it. You're not really changing the smooth manifold. All you're changing is the complex structure, which means if you take some differential, you might have some kind of surface, you take some dx, dy, and you're allowed to you have some notion of a holomorphic direction, and you have to take some particular linear combination of these dx's and the dy's. And it's important that these things are complex numbers. And so that's really what's changing. And another way of saying this, so there are many ways. The idea of a complex structure comes from differential geometry. Really, you should think about a tensor that squares to -1, which satisfies some properties. There's a formal way of saying this. But really, here what we want to study is what this does to differential forms or cohomology classes. So you can take on a Calabi-Yau threefold, you have the third cohomology with complex coefficients, and this will have some Hodge decomposition. So if you think of Durand cohomology, you take a differential form, and you can write it as a linear combination. If you have one form, you can write it as a linear combination of a holomorphic differential and an anti-holomorphic differential. And this idea carries on to the higher forms, and this eventually gives you a decomposition of your cohomology. And so you can take some reference cohomology class here and decompose it into its various parts, and then you can vary the complex structure and see how this decomposition changes. So the precise decomposition of a given reference cohomology class will depend on your choice of complex structure. It will depend on this parameter. And so the first example where you might want to study such things, there are lots of examples where you might want to study such things. Here I'll talk about two. The first one I'll talk about is these supersymmetric flux vacua. So on a Calabi-Yau threefold, you can have fluxes which really are just controlled by some three forms, and we want to consider their cohomology classes, and they have to be integral because the period should be integral, and that's just a condition of charge quantization. This comes from this RR. There's a phi form in 2B, and this is the NSNS free form. And I said that these deformations here, you have many deformations. I'm calling them Z alpha. There's some polymorphic three form for your Calabi-Yau. It will depend on your choice of complex structure, parameterized by these Z alphas. These Z alphas you can think of as the vevs of some massless scalars in 4-dimension. In the real world, we don't have massless scalars. The only scalar we have is the Higgs. It's not massless. So this is a problem for people interested in string phenomenology. And one of the most common ways of trying to stabilize moduli is by turning on these fluxes. They will generate a potential for these complex structure deformations. And it's this potential here. What you do is you take your holomorphic three form, you integrate it against your choice of fluxes, and there's some axial dilaton that appears in this story, this tau. And for there to be a supersymmetric solution, this Z alpha, your complex structure parameters, and the vev of this axial dilaton have to be at a critical point, a critical zero of this potential. Here, this means you can write down some covariant derivatives, and the covariant derivatives of this superpotential should vanish. And the potential itself should also vanish at these choices of complex structure moduli and tau. Here you have we'll see these covariant derivatives again, but just to say, your holomorphic three form is only defined, the overall scale of a holomorphic three form is not defined. On a Calabi-Yau threefold, there's a unique one, but it's only unique up to scale. And when your Calabi-Yaus come in families, you can, at every point, you can rescale your holomorphic three form. So this will have, this is called Z alpha. I can always redefine it by some nowhere vanishing holomorphic function. So ordinary derivatives wouldn't do here because this rescaling will not commute with an ordinary derivative. So you have a covariant derivative. Here, this function can be moved out past, will commute with this covariant derivative. As I'm sure many of you have seen before. And here you have to use a connection, which is the derivative of a Kähler potential on a moduli space. This second term is a Kähler potential on the space of complex structures of your Calabi-Yau. The space of complex structures on a Calabi-Yau itself is a Kähler manifold, it's a special Kähler manifold. This is the name people use. And we'll see this again in a minute. Okay, so this is an exercise for the listeners. Show that if these two conditions are satisfied, if your complex structure moduli and your tau are at a critical point of this potential W, then your fluxes, your F and tau, take some combination of them with controlled by this parameter tau. Then this particular combination will have a very specific Hodge-Lie composition. It will have no 3-0 part and no 1-2 part. That's just something you can show. And really, what you should do, I can give you a hint, is if you have some, say, F, you integrate it against omega, and this vanishes, well, this tells you that this F has no 0-3 part, because this is a 3-0 form. If this had a 0-3 part, you could make a 3-3 form, which is get something related to your volume form, and this should not vanish. So you conclude that your F has no 0-3 part. And you play these kind of games, and you can argue that this particular combination of fluxes has no 3-0 parts and no 1-2 parts. Moreover, if the potential is at a 0, then this 0-3 part will also vanish, and you're just left with something that's purely 2-1 plus 1-2. So purely 2-1. That then means that these F and H's, there you can take the complex conjugate of this, take linear combination, and just get the F and the H's on by themselves. When you take the complex conjugate of this, you'll get something with Hodge numbers 1, 2. So this tells you that F and H are integral or rational, both work. Integral homology classes with Hodge numbers purely in 2-1 and 1-2. So the fancy way of saying this is that your Hodge structure will split, and it will split off this 2-dimensional piece. Here, H3 of your Calabi-Yau will always have these Hodge numbers, always have a Q. Right? So the 3-0, there's always a unique class with Hodge numbers 3-0. Same with 0-3 versus complex conjugate. But then there are these Hodge numbers which give you the 1-2 and 2-1 part, and their dimensions are equal. And so the search for supersymmetric flux vacua is really a search for points in moduli space where the Hodge structure splits in some way. And this is a problem that people have looked at a lot in physics. There are some tadpole conjectures that have been made recently about when you can do this. Maybe you can't always stabilize all the moduli in this way. So it's an active area of research. The second physics motivation is this attractor mechanism, and it's a very similar kind of problem. So you think of 2B supergravity, again, this is in 10 dimensions. Your compact dimensions, you say are Calabi-Yau threefold, and in your uncompact 4 dimensions, like regular spacetime, you will have it will be asymptotically flat, but there will be a black hole metric. So you have some black hole in there. You make some assumptions. You say it's BPS, which means its mass saturates some lower bound. I'm not sure what everyone's background here is, whether they're comfortable with this stuff, but it's not so important. It's just the motivation. The problem will be cleanly stated. The black hole metric is controlled by some, it's spherical symmetric, so it's just controlled by some function u that depends on the radius, this warp factor. And it will have electric and magnetic charges, so it's PPS. There will be some gauge fields in 4 dimension, which is your third Betti number 2. So there will be this many types of electromagnetism, and for each of those electromagnetisms, this black hole will be charged. So we'll have some electric and magnetic charges. And another way of saying this is that this gamma will be the dual of some homology class wrapped by a D3 brane. Again, if those words don't mean anything to you, don't worry, it's not so important. Well, it's important, but not for here. And there will be a central charge function, which is a lot like this this potential that we met in the story with the flux compactifications. Here, this central charge will give you the mass of your black hole. And it's an integral over your compact space, over the Calabi-Yau. Take your polymorphic 3 form, integrate it against your charge vector, and you have to normalize the whole thing by this scalar potential. Here, this K is the one that we met earlier, without the part involving the axial dilaton. And the name attractor mechanism comes from usually when there is no black hole, your spacetime is just flat. Your moduli can basically take whatever value you like. They're unconstrained. But in the presence of a black hole, something strange happens. Infinitely far from the horizon of the black hole, your spacetime is flat, and your moduli can basically take whatever value you like. But as you flow towards the horizon of your black hole, which is this R equals 0, it will have to take a very specific profile, and that profile is controlled by this differential equation. So mu is some radial coordinates. This G is a metric on your space of complex structures. We saw the scalar potential earlier, so you just take derivatives of the scalar potential. That will give you the metric. And this differential equation will define a flow on your space of complex structures. And this can be another exercise. You have to use an identity from special geometry, which we'll see later on in this talk. But you can show that this flow will have some fixed points, and the fixed points will be precisely will be the points where your gamma, which is like a charge, which are the charges of your black hole, this charge vector will have a very specific Hodge decomposition. It will have no 2-1 part or no 1-2 part. And remember, the Hodge decomposition depends on your choice of complex structures. So this singles out some point in your complex structure moduli space. And if we have 2 linearly independent, gamma 1 and gamma 2, that both have this Hodge decomposition at the same fixed point, we say that this fixed point is an attractor point of rank 2. And so this is an example of the kinds of flows. So these are things you can compute. You can put them on a computer, you can compute some periods. We'll see this in a second. And you can find these flows. And you'll see that these are for different choices of charges, and they lead to the same fixed point. And you can also see why it's called the attractor mechanism, because here there's a single complex structure modulus, which it's called phi here. Phi can start from here. It can be wherever, infinitely far from the horizon of the black hole. It can be wherever you like. But as you flow towards the horizon of the black hole, it will always flow to the same fixed point. That's why it's called the attractor mechanism. And you see, these are really 2 different flows on the moduli space. You can see they are different in this region. but they have the same fixed point. So this fixed point is interesting. It's a lot like this. So it's a lot like a supersymmetric flux vacuum. When H21 is equal to 1, it really is the same thing. Okay, so we have these problems that come from physics. We want to find special points in moduli space where some integral, so the integrality is important, or they can also be rational. It really, they should be integral, but the problem also makes sense if they're rational. Where some cohomology class has a specific Hodge decomposition. So we want to find these special points in moduli space. And as I said before, these problems are quite similar. You know, you take some reference cohomology class at some random point in moduli space, it will have a very specific Hodge decomposition. It will have this, you know, it will have some to 0 parts, some to 1 part, some 2 parts, and some 0.3 part. But at these special points, there will be some integral or rational cohomology classes that have precisely these Hodge numbers, and there will be 2 of them. They will give you this 2-dimensional piece of a motive. And a tractor point of rank 2 is very similar, but the 2-dimensional piece that splits off will have Hodge numbers 3, 0, and 0, 3. And you can see that when H21 is 1, they're the same. Right, you will just have a 1, 0, 0, 1 parts here, and this will be. And these will be the examples we will study because they're the simplest one where you can compute stuff. But you can compute plenty when H21 is not equal to 1, it's just more difficult. And the way we study these problems, the way we study these variations of Hodge structure, is we use periods. And this is a very active area of research. There are probably experts in the audience that can tell you more about this. But that's mostly the physics motivation for why you should study these kind of problems. How are we doing time? Are there any questions? Nope. All right. Well, I'll move on with very disconcerting when everyone's silent. Okay, so the simplest finding these points in moduli space where the Hodge structure splits is a lot like a very classical problem. It's you can search for elliptic curves with complex multiplication. This is something that's very well known, and it's basically a baby version of the kinds of problems you would have to study when you are looking for supersymmetric flux vacua or these rank 2 attractors. So I think it's instructive to look at this example in detail and just explain what's different when you study Calabi-Yau threefolds. Okay, so the most basic example of an elliptic curve, a family of elliptic curves over the complex numbers, is this Legendre family. You have your x, y, z, their coordinates in the homogeneous coordinates in P2, and you study this curve that's defined by this equation, and it will have a parameter, this parameter lambda. So topologically, this is a torus, and it will have 2 1 cycles, and they're relatively easy to identify. Sorry, I wrote this down. So you go to the z is equal to 1 patch, and you have y is x minus 1, and x minus lambda. And you want to try and understand this space of solutions. This y has a square root, so it's multi-valued. So really, your elliptic curve will be 2 copies of the complex plane, or the P1, glued along branch cuts. So you can have, if you imagine your P1 like this, and then there's some this 0, your lambda, your 1, infinity. All right, these branch points, or at least the ones that aren't infinite, are just the solutions of this, where y is 0, and the 2 branches come together. Infinity, 1, and they should be glued along these along here, and along here. It's an awful picture, but I hope you can see that this is topologically a torus. And what's more, you can identify cycles on this picture. So you can have your A cycle here. And you can define a B cycle by on this picture. And when you cross this branch cut, you end up on the other copy. That's what these dashes are telling you, like you're on the other branch. So this A and B cycle will only intersect once. And that's kind of obvious when you think about it on this picture. This is terrible. Okay. So we have some one cycles. They give you the homology of your elliptic curve at lambda. And we also have a polymorphic one form. So this can be an exercise. Show that this is a no way vanishing polymorphic one form on the elliptic curve, or that it extends to a no way vanishing polymorphic one form on the elliptic curve. You have to use the fact that the elliptic curve is smooth. This is an exercise. And we can explicitly compute its periods. Sorry, this is an earlier version of these notes. I should write pi 2f1 half 1 lambda, and this is a minus I 2f1 half 1 lambda. And the point is that we have these A cycles and B cycles that we wrote down earlier. We have a holomorphic one form. We integrate them, we'll find some functions of lambda. And their functions, they're very famous functions. They're Gauss's hypergeometric functions. Should be 1 minus lambda. And these have been implemented, for example, in Mathematica. They're very classical things. And the holomorphic one form can now be expressed as a cohomology class using these periods. So you take your A and B cycles, and they will have some duals, which I call alpha and beta. They define in this way. They also satisfy alpha, which beta, it's 1. And so, okay, so you have some integral homology classes. You take some particular combinations of them to get a holomorphic one form, and the precise combination you take depends on your parameter lambda. And so we can express our holomorphic one form as a cohomology class in some nice basis, alpha and beta, and the coefficients are these functions, these periods. And it's important that they're complex. So you should think of these functions, these pi0 and pi1, as homogeneous coordinates on the moduli space of elliptic curves. They're homogeneous because, as you saw before, the normalization of this holomorphic one form isn't fixed. I can always multiply it by something. And so yeah, I pick some function here. This is still a holomorphic one form. So these should be thought of as homogeneous coordinates, and their ratio is an inhomogeneous coordinate. And it's, if you know anything about elliptic curves, you've almost certainly seen this tau before. And of course, this imaginary part of tau will be in the upper half plane when it shows out like this. And we say that an elliptic curve with parameter lambda has complex multiplication if tau is a solution of some quadratic equation with integer coefficients. It's a very classical thing. So when your elliptic curve has complex multiplication, we have a holomorphic differential. So it has large numbers, a homomorphic, a 1,0 cohomology class. This is 1,0 because remember our holomorphic one form was pi0 alpha plus pi1 beta. The normalization isn't fixed, so I can free to divide out by this. And this is just alpha plus tau beta. This is a holomorphic differential, so of course it has Hodge numbers. It will have Hodge decomposition 1,0. So what we found is a cohomology class with Hodge numbers with a very specific Hodge decomposition. The only difference between this case, well, the major difference between this case and what we were looking for when we were thinking about supersymmetric flux vacua is that here the coefficients are, you have to use coefficients that are in q squared to minus 3, right? These are integral classes, but you have to use coefficients in this extension of q. So it's almost the same problem, but not quite. It's a relatively minor difference. I think the techniques are the same. The techniques you would use to study one are the same as you would use to study the other. Okay, so we found a splitting for some. Suppose we found such a tau, such a lambda where tau is valued in this field extension. At these points, we have a splitting over an extension of Q. We have a cohomology class with coefficients in this extension with very specific Hodge numbers. You know, this spans this part, and its complex conjugate will span this part. And yeah, so this is a baby example for this is a toy example of the kind of problem you would have to study when you're searching for supersymmetric flux vacua or these rank 2 attractors. And I'll move on to what's different about Calabi threefolds, but this is a good time for questions. There's something in the chat. Oh, hello. Hi.
Yeah, I don't see any questions.
I
I'll
have
let
a
you know if
question.
there is some questions in the chat.
I have a question.
Yes,
Can you
go
hear
ahead.
me? Hi. In this case of Calabi threefolds, we were limited for only one parameter Calabi.
In principle, no. But I think the computations are just more difficult when you have more parameters. But no, I think everything I say should apply to multi-parameter Calabi-Yaos as well. It's just that examples are more of a pain, but there are some in the literature. It's just hard work. Instead of studying a ODE, when you're computing your periods, you end up studying a system of PDEs. That's more difficult. But that's basically it.
Okay, thank you.
Sure. I'll move on to the Calabi threefolds. Albrecht spoke about this in his talk, so I'll repeat some of what he said. Actually, a lot of this overlaps with his talk, so hopefully you'll benefit from both explanations. So for Calabi threefold, we have a nice homology basis. You know, for an elliptic curve, we had these A cycles and B cycles. We saw earlier. On a Calabi threefold, you can find something very similar. Some nice bases with certain intersections. You will have 1 plus H21 A cycles and 1 plus H21 B cycles. And as before, we can compute periods. So there's some polymorphic free form you can write down. There's some algebraic thing. And here I'm going to assume that H21 is equal to 1, just because it makes the cut. These are the examples I can show you because they're. And so to answer, Felix just asked, what's different? It's not much will be different when H21 is bigger than 1. It's just that solving these PDEs become a pain. But in principle, if you're willing to work, it's everything that I say will apply there as well. So you compute these periods, but in practice, if I give you some Calabi threefold, finding some bases of 3 cycles is way too difficult. Unless maybe sometimes your Calabi has some nice vibration structure, which you can take advantage of and identify 3 cycles. But in practice, it's too hard. Generally, it's too hard finding some nice bases. So you use a trick. First, you note that this pi satisfies the differential equation. This is what Albrecht mentioned, and it's a very important fact. This just follows from, it's a simple argument, omega is in H30. Well, sorry, it's a 3 class. You can differentiate with respect to complex structure. That will still give you a cohomology class. And you keep doing this, you take 4 derivatives, you still have another cohomology class, but now you have 5 classes, but B3 is 4. So there should be some relation between them. There should be some linear combination of them that gives you an exact form. And you can integrate this. The exact form will integrate to 0. And this linear combination that you take will have this precise linear combination you have to take will have coefficients which depend on your parameter phi. And that's just a differential equation. So that's how you argue that there should be a differential equation. It's a famous one. It's Picard-Flux equation that annihilates these periods. And here's an example. It's this complicated looking thing, but it's a linear ODE. It's a 4th order. It's the kind of thing you would learn to solve in a class on ODEs. I'm sure many of you have seen something like this in your undergraduate classes. And this particular one has a name. It's 34, and this AE-Z list is for Almquist, Enkevard, Van Straten, and Zudillen. Picard-Flux equations are very important things. There's a lot you can do with them. You can study topological strings, and there's also a lot of arithmetic geometry that comes from these differential equations. So they thought, look, these things are important. Why don't we try and compile a list of all known ODEs that could be the Picard-Flux equation of some family of varieties. And that's this huge table. There are hundreds of these things. Duco maintains a database, which you can search for on Google with a computer. And this one is 34th on the list. Just pick one. This one has nice properties, and it will have some of these rank to attractors. All right. When you solve this differential equation, the difficult part is that you can use this method of Frobenius to solve this, but it will give you a basis of solutions that doesn't correspond to integrating over some nice integral symplectic basis. When you integrate over this thing, this pi will have monodromy, which is valued in SP4Z. So this has monodromy in SP4Z. This SP4Z is really just a consequence of this relation. Right, such a base is only defined up to these, I think that's Albert mentioned, only defined up to these transformations. But you can use a trick from mirror symmetry to find a nice basis. And because we're really interested in like the integral structure of our cohomology classes, it's important that we have such a basis. But fortunately, there's a trick from mirror symmetry, and this goes back to a well-known paper of Candelas, De La Osa, Green, and Parks. And so the solutions that you would find if you use the techniques from your undergraduate ODE class is something like this. You have these FKs, these are power series, and they're going to be multiplied by some logs. You plug in this ansatz into your differential equation, and you normalize it in some way. You say F0 has leading term 1, the other ones have leading term 0. That's just an arbitrary choice you can make. And when you normalize them in this way, you can plug this into your differential equation, find recursion relations for the coefficients of these power series. And okay, this is something you can put on a computer. In the simplest cases, you can exactly solve these recursions. You can find out exactly what these things are. There will be something like hypergeometric functions when there is only one singularity. But in order to guarantee that your monodromy is an SP4Z, you really need this trick from mirror symmetry. And it'd be too time consuming to explain where it comes from. I would just show you this matrix and guide you towards the literature. And you can search for gamma class. That's been a popular thing recently that explains some of these numbers. The point you should take away is that really there are 3 integers in this matrix. There's the Euler characteristic of the mirror manifold. there's this triple intersection number. So there's some class which generates H2 of the mirror, and it will have some triple intersection number. And there's second Chern class. If you have this topological data, you can fix the diffeomorphism class of your Clavial, but of the mirror, and this also fixes the same numbers also fix this nice integral symplectic basis for you. Something you can do, which is a nice trick, that was used by, for example, Dukov and Stratton with, I think, Enkefart. You can just make an ansatz for this matrix. Numerically compute the monitoring matrices of your you just make an ansatz, you plug this in, you numerically compute the monitoring matrices for this, and then you say these should be integral, and these give you strong constraints on these numbers. And usually you can fix them up to a hand if you're willing to trust some numerical computations, but you should be able to fix them up to some handful of possibilities. You know, at the end of the day, you're looking for integers, and one decimal place is enough to identify an integer. And so really, if I just give you a Picard-Fuchs equation, if it's an ODE, it's one of these ones that comes from these fourth order ones, you can go quite far with just the ODE and some numerics. Okay, so we're almost there. Let's see. We're almost there. We're almost able to compute the Hodge decomposition of some cohomology class at an arbitrary point in moduli space. We just need one more trick. This comes from special geometry, which tells you about the moduli space of these Calabi-Yau have some very nice geometric structure. This is explained in this paper of Strominger. I also really like this paper moduli space of Calabi-Yau manifolds, which is quite down to earth and explains many of these constructions. And I mean, by now you can find this stuff in textbooks. So the trick involves differentiating your holomorphic differential with respect to some parameter. So if you go back to the elliptic curve case, you know, or some curve, there's some combination of these dx's and dy's that you take to get something holomorphic, but then you differentiate with respect to this parameter. You know, the dx part gets killed. You end up with a derivative of this tau and this dy. But then the dy can be written in terms of this dz and dz bar. So it's a very simple demonstration. You know, when you differentiate a 1-0 form with respect to complex structure, you pick up a 0-1 part. So you do the same thing with your holomorphic 3 form. You differentiate this thing, which will depend on your parameters, but these things are supposed to be holomorphic differentials, and so they will also depend on your complex structure. Your complex structure is what determines what's holomorphic. And when you differentiate this, as we saw, we pick up a 0-1 part. So you end up with a 0-1 here, and the remaining 2-0 parts, and that's how you generate a 2-1 part. And this is as a cohomology class. And so this is some standard fact. And really, you can then go back and try to delete this 0 part, so you just end up purely with a 2-1 cohomology class. And this is what some tricks from special geometry allow you to do. So you define these covariant derivatives. And as before, the job of these as I explained earlier, the job of these covariant derivatives, there are different ways of thinking about it, is, well, in this case, I think the best way to think about it is this omega is really some section of some line bundle. It's only you can rescale omega by some holomorphic function, at least in some local patch. And you want, so differentiating these things that have gauge transformations is, really should be done with the covariant derivative. And that's what this covariant derivative does. This rescaling will pass commutes through this covariant derivative. And as it's the same one that we saw earlier, the connection here is given by the derivative of some Kähler potential. And the Kähler potential you can compute from the periods. So everything comes from these periods. And this sigma is, I think Albert also mentioned, I'm sure he did, this standard symplectic matrix. And this is essentially some generalization of these Riemann bilinear relations. So you can compute some integral you can compute this kind of integral if you know the periods. And if you know the periods in a very nice basis, that's what really the power of having this integral symplectic basis. You get these Riemann bilinear type relations. Okay, so I promised examples, and here is an example. So you numerically just compute this the periods of some polymorphic. I use some topological data to fix this, and they had these three numbers in this matrix that we saw earlier. And yeah, you can just analytically continue however you like. These things are not so difficult to do on a computer. Oh, there's a very nice package called Aura Algebra that Ilya told me about a while ago. It's in Sage that will do many of this computation, that will help you with lots of this analytic continuation. I know there are some Perry experts, or maybe I don't know if you can do this in Perry. So you have some differential equation, you find some solutions, you can analytically continue numerically, and when you get to this special point, the periods will have a very special structure. They will be just complex linear combinations of these integral vectors, and this tells you that you're at an attractor point of rank 2. So you can just check that this particular vector, you take the product with the periods, and this will vanish. At least numerically will vanish. You can check the thousands of decimal places, and then you believe, okay, this really works. It's not a proof, but probably good enough. Remember, we have these Riemann bilinear type identities, which say that there's some class gamma. This is just this kind of expression is really an integral. Is 0. Gamma is an integral class, so you can take the complex conjugate. And look, what this is telling you is that gamma can't have a 0,3 part, because if it did, then this would be non-vanishing. Gamma, again, can't have a degree 0 part, because then you create something proportional to a class of the volume form, and that would be non-vanishing. So you argue that these two identities, well, this identity tells you that there's some cohomology class with Hodge numbers purely 2, 1 plus 1, 2. And that's what this is. That's this 3, this 3, this 6, minus 6, this minus 6, and so on. So you have a class integral purely with Hodge numbers 2, 1 plus 1, 2, if you believe these numerics. You can check to thousands of decimal places. So unless something really unfortunate is happening, it's probably good. And also there are other checks that you can make. And you can play around with the covariant derivative and do something very similar. You find some classes, they, when gamma, wedge, phi, omega, like this expression, you should think of as this integral, and they're equal. And remember, we said this has Hodge numbers 2, 1. So you argue as before that this gamma cannot have a 1-2 part. You take the complex conjugate, you say it can't have a 2-1 part. So you find a class with Hodge numbers purely in 0 plus 0, 3. And that's what we needed for these attractive points of rank 2. And we have some splitting of Hodge structure. It's some analog of complex multiplication for a Cauda threefold. And yeah, all of this you can do on a computer. If you just compute these periods, you know some trick from mirror symmetry, and this is something most PhD students can go away and do. Okay, so we know how to numerically at least verify that some point is in the moduli space is an attractive point of rank 2, or you can say supposed to flux vacuum. Everything I said should generalize to the multi-parameter case. And we know how to study Hodge decompositions at arbitrary points in moduli space. But I didn't explain how we found these points in the first place. And that you can brute force it. The Neff famously tried. He wrote some code, tried to find these points on the quintic just by brute force. It didn't work, and now we believe the quintic doesn't. If it does have these special points, they're more complicated. Yeah. Now we kind of understand why he failed on the mirror quintic. And we understand this because we know we have these techniques from arithmetic geometry. And I will explain this trick. I'm running out of time, but unless there are questions, I should explain the trick. All right, I'm gonna move on. Okay, so the tool we'll use from arithmetic geometry is the zeta function. So if you have some polynomial defined over Q, so you say this parameter psi is Q, or really it can be algebraic as well. Algebraic is good enough. You can reduce this mod P and say, well, these xi's are in FP or FP to the R. So some extension FP is just 0, 1, da da da. And then you take some field extensions of this, you know, you take some quadratic, you could take some degree D polynomial, which doesn't have solutions in this, you add them on, and just define FP to the R. And you can define a zeta function. This is a very famous object that was studied a lot in the 20th century and still continues to be studied. And this is the subject of these famous Weil conjectures, which are now theorems. And they're natural objects. They're generating functions for these point counts over finite fields. And they have some very special properties. So if you're a number theorist, this is all very old to you. If you're a physicist, you probably won't have seen something like this before, but it's a useful object. One of the Weil conjectures said that these things are rational, and these things are rational functions of this parameter t. And these coefficients, they have some meaning. Each of them, of course, these polynomials, sorry, have some meaning. Each of them corresponds to some cohomology class. It's the characteristic polynomial of some Frobenius map, which I will not explain. Just I have little time left. But yeah, they're characteristic polynomials, so their degree is given by the Betti number. And that's the only one we'll need. And you have the zeta function for every prime. So this sum is over extensions of FP. And you can define a passive Weil function for each of these polynomials. So you just multiply them over all the good primes. Good primes mean when you reduce mod P, you still have something smooth. And the most basic example is the zeta function of a point. So just to convince you that these aren't so wild. Yeah. For a point, np to the r is always 1. You take the sum, you get some logarithm, exponentiate, and you get a rational function as promised. And you define the L function by taking products of all these, and you make the replacement t with p to the minus s, and you take the product over all primes, and this is just the well-known Euler factor formula for the Riemann zeta function. So the zeta function of a point is the Riemann zeta function. And then you can move on to more complicated examples. An elliptic curve, this is a very famous example, will have a zeta function. Remember, an elliptic curve has b0 is 1, b1 is 2, and b2 is 1. So you expect a first order polynomial here, first order polynomial here, and a quadratic polynomial in the numerator. And most of these coefficients are fixed by some of the other Weil conjectures, except for this one number, AP. And AP is going to be some integer. And it's related to point counts over finite fields of your elliptic curve. And you can define an L function for the as before by taking products over all primes and making the replacement p to the minus s for this t. And these APs are Fourier coefficients of modular forms. This is a very famous thing, very famous observation. A modular form is something polymorphic in the upper half plane. It doesn't grow too quickly at the cusps. So at the boundaries of the upper half plane, the rational points at infinity. And it transforms in a very nice way. And so this will have some weights associated with it and a level. So to the experts who know this very well, I apologize, but this is supposed to be an introductory lecture. Okay, so we have this for elliptic curve, and it was very famously proven that these coefficients come from modular form. Modular forms of weight 2. This is this modularity theorem. So when Andrew Wiles proved Fermat's theorem, he proved the special case of this theorem, which then was finished by him and his students. It's a very important object, very, very important result in arithmetic geometry. And it'd be good to know what this means for the kinds of problems we've been studying. But right now I should be quicker and say that the zeta function of a Calabi threefold with h21 is equal to 1 can be shown to be, this form. The only interesting part is, the really interesting part is this numerator corresponding to h3. So we had b3 is 4. You get fourth order polynomial in this numerator. And we want to study attractive points of rank 2. So you can Q is also fine here. Q, so then this becomes equality, and you find some vector spaces which very specific Hodge numbers. And the point is that this kind of factorization, this kind of decomposition will be visible in the zeta function as a factorization of this numerator. Why this would require explaining what these things really are, which I didn't. They're characteristic polynomials of some map on some Ital cohomology. And when you have this kind of decomposition, you can block diagonalize these matrices, and that's why this characteristic polynomial will factorize. That's the hand-wavy explanation. Maybe it's for someone else to explain. I will move along. And the point is, this is the kind of thing you can look for. You can study on you can put on a computer. You can, you have a family of Calabi-Yau threefolds. You can compute these. In principle, just do the brute force point counting. In practice, that's way too slow. There are tricks that have been developed that let you compute these much more quickly. And you can compute these APs and BPs and try to factor this polynomial over the integers. This is something you can do on a computer. And that's an effective strategy for trying to find these special points. So what you do is, so there's lots of work that's been done to compute these things quickly on a computer. Once you can do this, what you can do is compute these polynomials for all phi, you say your parameters phi in FP, and you do this computation for any p. And what you look for is some polynomial. You make some ansatz, and you say, whenever, I fix a polynomial, I solve it mod p, I find the solutions phi, and at these solutions, I should be able to, for this particular phi, I should be able to check the zeta function and confirm that it factorizes. And if I found such a thing, I believe I found an attractive point of rank 2, or flux, supersymmetric flux vacuum. And when H21 is 1, they're the same thing. And so what you do is you use your computer. You go over many primes, and you count how many phi in FP, such that the Frobenius polynomial factors. And this is for this example. A is at 34. This is, you had the special point at -7. And this second plot is for the mirror quintic. And you can kind of see just by eye that A is at 34, has lots of factorizations. So this family should have these special points. Well, if you just believe you would strongly suspect that it has these special points. Whereas the mirror quintic, doesn't factor so often. Some factorizations you would just expect at random. And so just by looking at this, it's no surprise that Denef was unable to find these special points. He was motivated by a paper of Greg Moore, where Greg pointed out that these attractive points of rank 2 are very often interesting arithmetic objects. So if your Calabi-Yau is a product of 3 elliptic curves, then the elliptic curves will have complex multiplication. If your Calabi-Yau is a K3 times T2, you get very special K3, and the elliptic curve will also have complex multiplication. And so they wanted more examples, and Denef and Greg suspected, Denef and Moore suspected that these rank 2 attractors were special, but they were unfortunate in that they decided to search in the mirror quintic, because we now see that the mirror quintic doesn't have so many of these factorizations, so it's unlikely you'll find a point. Whereas some other examples, like this A is at 34, have lots of factorizations, so you expect to find these special points. And yeah, indeed, you find a third order polynomial, and at the solutions, you expect attractive points of rank 2, and you can confirm this using techniques of the periods that I explained earlier. And yeah, so that's how we were able to come up with -7. And now the mysterious part. In this Frobenius polynomial, you have these modular forms. So okay, here's the modular form, its coefficients, tell you about point counts, or actually you need both of them. You need the weight 4 and the weight 2 one. Their coefficients tell you about point counts over finite fields, when phi is minus a seventh. And if you don't know this, a very useful resource when studying modular forms is this L functions and modular forms database. It's a website which has any modular form you can think of, and they've named some of these modular forms. So the weight 2 one has this name. It has level 14, weight 2, and the weight 4 one also has the same level, 14, and this is its LMFDB label. For anyone interested in this kind of work, I strongly recommend LMFDB. Okay, and what can all this mean physically? Well, the arithmetic geometers believe that you should be able to, for good reason, believe that you should be able to see these L values in periods. So you can take the Mellin transform of some modular form and evaluate that special critical points, critical values. So in this case, it's 1, 2, and 3 for a weight 4 modular form. I won't explain what critical value is. I will just say that these numbers that we saw earlier that we computed numerically, you can identify, well, you can conjecture exact expressions for in terms of these critical L values. So you take your weight 4 modular form, compute the L function, evaluate it at these special points, 1 and 2, and you see these numbers in the periods. And the same thing for the weight. For the 2-1 form, 2-1 the 2-1 plus 1-2 part is associated with it's like the homology of an elliptic curve times a P1, and the elliptic curve will be modular. It will have some weight 2 form associated with it, and that's why you're seeing this weight L values of critical L values of the weight associated with the weight 2 modular form in these covariant derivatives. And there's another number, which is tau of this elliptic curve, and you can conjecture exact expressions. Okay, but what does this mean physically? Well, the best clue we have, I believe, is this formula for horizon area of black holes. We can compute this in terms of the periods, and so you have a rank 2 lattice of possible charges that this black hole at this attractor point can have. You take any linear combination of these, the black hole, the associated black hole will have horizon area given in terms of these L values. And well, that's interesting because the horizon area of black hole is a measure of entropy. So there should be some kind of microstate counting for associated with this black hole. And that should know about these critical L values. And then you ask, well, why do these microstates know about these modular forms? Is there something deeper going on? And that's an open question. I encourage students to investigate, and I think that's my talk.